In this video, we're going to find the local minimums, local maximums, and saddle points of this function f of xy equals x squared y plus 3xy plus xy squared. Now, we're going to need to find out when the partial derivative with respect to x is equal to 0 and when the partial derivative with respect to y is 0. If you compute the partial derivative with respect to x, you should get 2xy plus 3y plus y squared. And for partial with respect to y, this should be x squared plus 3x plus 2xy. We're going to have to set each of these equal to 0, of course. So let's do that. Set that equal to 0. Set this formula for partial with respect to y equal to 0 as well. I think the easiest thing to do here would be to just factor out a y, and then you have y times the quantity y plus 3 plus 2x equals 0. Same deal over here, factor out an x, and you'll have x times quantity x plus 3 plus 2y equals 0. If you split this into two separate equations, you'll have y equals 0, and it's probably a very good idea to put this here, the word or, y plus 3 plus 2x equals 0, and same thing here, either you have x is equal to 0, or you have x plus 3 plus 2y equals 0. And I'll go ahead and create the kind of overall mathematical sentence we need. We need something from over here or something from over here to be true. So one of these two things should be true, and then one of these two things over here should be true. So mathematically, we have this and right there. And you can actually treat this sort of like a menu thing where we actually need, say, one from each list to be true. So it could be the first option from each, and then you'd have x is 0 and y is 0. So this tells us that xy, excuse me, let's leave that out. This tells us that the xy 0, 0, that point is an example of a critical point. But we could also have this combination where y is 0 and x plus 3 plus 2y equals 0. Now what's the solution to that? Well, if y has to be 0, you plug in y equals 0 over here, and you just get x is equal to negative 3. So we get negative 3 comma 0. And that's all we're going to get using y equals 0. We've looked at each of the options over here, but then we can take the second equation over here and the first equation over here. Now x is equal to 0, so plug in x equals 0 here, and then you're forced to see that y is equal to negative 3. So 0, negative 3. And then finally, you could combine the last equation over here with the last equation over here. These are actually the graphs of two lines, and they I won't go through the details, but they happen to intersect at negative 1, comma, negative 1. And that's really it. So you can mix and match each one of these two with one of these two, and you get these 4 critical points. So these 0, 0, negative 3, 0, 0, negative 3, and negative 1, negative 1. These are the only critical points. Points for this function f. And now our goal is to figure out what kind of critical points we have in each case. We're actually now done with the information from here, so let's get rid of this stuff. We're not going to need that anymore. And let's bring our critical points up here a little bit. Now, what we'll need to do is compute the discriminant or the Hessian. That's going to call for finding the partial derivative with respect to x a second time. So based on the formula for fx right there, we would get the second partial derivative with respect to x as 2y. In the same way, looking at f sub y, the second partial with respect to y is going to be 2x. And finally, we are going to need to take fx and compute the derivative of that with respect to y. You'll get 2x plus 3 plus 2y if you do that. And actually, due to Clairaut's theorem, because f is continuous, you're actually going to get, this is going to be the same as f sub yx as well. So that's all we need in order to talk about the discriminant or the Hessian. So this will be a function of two inputs, and we'll take the determinant of, well, copy the 2y from right here, and then we'll need in the off diagonal entries here 2x plus 3 plus 2y, same thing again, 2x plus 3 plus 2y, and then finally over here 2x. And this may look daunting to compute, but I'd say let's go ahead and multiply these two out and simplify. We'll have 4xy and then minus, and here I'd say let's not really worry about simplifying. just write this as 2x plus 3 plus 2y quantity squared without worrying here about using the distributive rule at all. So there's our function capital D, and now what we should do, we're done with the use of these functions, though we should hold on to fxx just in case, so let's leave that up here somewhere. But we should take our critical points and now run them through the discriminant or Hessian that we computed to see what kind of critical points we have. So let's take d of 0, 0, the first critical point up here. And I won't go through all the careful plugging in of x and y being 0, 0, but you should get something like 0 minus 3 squared, which is negative, and this is going to lead from the second derivative test to 0, 0 being a saddle point. So this is a saddle point. If you look at d of the next critical point here of negative 3, 0, you should get something like 0 minus negative 6 plus 3 quantity squared. I won't go through again all the details. That's negative, and therefore by the second derivative test you have negative 3, 0 is another saddle point. And actually symmetrically the arithmetic works out the same. D of 0, negative 3 is also going to be 0 minus negative 3 quantity squared. So this number negative 9, well, that's negative, and being smaller than 0, we're going to actually conclude that 0, negative 3 is yet a third saddle point. Does something interesting happen in the last case? It sure does. Let's compute d of negative 1, negative 1. And when you do that, I got 4 minus negative 2 plus 3 minus 2 quantity squared, or 4 minus 1. Hey, that's 3, that's positive, meaning that negative 1 is either a local min or a local max. To figure out which, we're going to have to go to looking at fxx, so that's why we kept this up here. We'll plug in negative 1 for any x's and negative 1 for any y's into the formula 2y. Okay, well, we just have to plug in for that negative 1 right there and get the number negative 2. Since this is negative by the second derivative test, we get that negative 1 is where a local maximum is located. I think the best way to say this, to follow the terminology of calculus books, is to say that f has a local maximum at negative 1, negative 1. I've switched over to Desmos.com, the online calculator, and typed in the formula for our function right here, along with, to get some level curves, I've actually put into square brackets negative 1, comma, negative 0.9, then dot, 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 then a 1, and then a right square bracket. And so you see a bunch of different level curves here. Unfortunately, they don't show up in different colors. And you can actually see from the crossing lines right there, that's actually all part of one level curve. We'll highlight this in just a second, but there's 0, 0, one of our saddle points. There's negative 3, 0, another saddle point. There's 0, negative 3, our third saddle point. And negative 1, look right there, that's actually going to be our where that local maximum occurred. So let's actually look at a certain level set at a time. So let's look at all of the inputs xy which have an output of 0. That's why the k equals 0 is right there. And now you'll see in blue, all along here, you'll see that actually the function is 0 all along this horizontal line and along this piece right there, and then along this diagonal line right there. And just to give away a little bit of the punchline, what happens is you see this triangle encased by this blue set of line segments, and as we see k get bigger, as we look at bigger outputs, you'll see these ovalish shapes being highlighted until we get to the very peak right here, which isn't highlighted very well by the computer, and therefore these other regions out here will correspond to these other regions will correspond to lower values. So you see increasing values of the output this way and that way from where -3 is, and you'll see decreasing values that way and that way. So let me go ahead and play this. And so you'll see what's highlighted in blue right about now is the biggest values, and then there are more and more negative values, but though I've only asked this computer to give you values up to -1 for the output. But take a look again. We just passed by those saddle points, and there's a local maximum. Now we're looking at each moment in time, we're looking at values of z being smaller, and like if I pause right here, for instance, I got lucky. Right now in blue, you're seeing highlighted all of the inputs to the function where the output is equal to -1/2. And if I keep playing again, right at, let's see if I can catch it, did not, but right at, very close to here anyway, you'll get, there it is. These are all of the points. Let me zoom in a little bit. Okay, the computer's highlighting for us right now all of the places where the output happens to give 0, which inputs give an output of 0, and we'll play this a little bit longer. And let me just pause again right about here. Okay, there we go. We did fairly well. So -0.99, all of the points along this little blue oval have an output value of 0.99. And if I scoot this all the way over to 1, I don't think the computer will give the point right at the top, which is -1, but that is a peak. Yeah, it went away. That's just a little issue with the computer. There really is just a single point right there where the output is +1, and that's why this is a local maximum. All around there surrounding, you have otherwise values of the output that are like 0.97 or 0.95 and so on. Our particular example today did not have any local minimum points. Of course, if we go back to our work here, that would just be because we only got one local min or local max due to the d function here being positive. And if hypothetically f sub xx for a critical number happened to be a positive number, then we would have seen a local minimum as well.